Thank you very much for giving me this opportunity. From Mizuho Research and Technologies, I'm Uno. Today, I would like to talk about with the title of Toward the Application of Quantum Computers in the Financial Field. In Mizuho, we are working for the research on quantum computers for financial field. So that's what I would like to talk about. So first of all, let me introduce you this Mizuho Financial Group where I belong to. In our group, we have bank, trust banking, and securities asset management think tank. So it is a comprehensive financial company. We have one slogan that is One Mizuho. So for the bank, trust, the securities, each group are working in a unified manner, so that we can contribute to the development of customers, society, and also the economy. So we were working very hard for that. And what's the positioning of a quantum computer within Mizuho? We have digitalization efforts taking place as a company as a whole. Mizuho views changes in the environment as opportunities to create innovation. And we are working for the open collaboration with outside so that we can meet the needs of the needs of the customers in next generation. You can find the charts toward the bottom. Our strength is the customer information foundation, and also knowledge of the finance and technologies are combined so that we can solve social issues, create new business, as well as upgrade the existing services. Out of these technologies, most important new technology is quantum computer as various options, and that is where we are now pursuing for the R&D. Here is our approach. Mainly, IBM Quantum Network Hub at KO is the venue of working for the research. IBM Quantum Network Hub, well, Raymond-san is going to give us the presentation later on. But there's a finance team, and that's where I also work for. Here, the KO University member companies, IBM, gather together to work for the financial-related issues. Member companies are described here: MUFG, SMTV, Sony, Hitachi, and ourselves, Mizuho. So member companies propose the actual issues built by each company, and IBM come up with the hardware and the technical support. And the KO University also join so that in collaborative manner we can solve the issues proposed. That's the approach that we are taking. One of the characteristics of this finance team is that as a background of the researchers, not only quantum computing, there are many with different backgrounds gathered together. They come up with the knowledge and ideas to solve issues. This is the overview of finance team research. Main theme of the research is these four: simulation, optimization, machine learning, and cryptography. Regarding simulation, let me explain using from the next page. So elaborate price evaluation of derivative. And for optimization, that is the asset distribution and optimization of the trade path. And for machine learning, the trade information or data or machine learning for that is currently proceeded. Cryptography, this is for the protection of the customer's information when it is possible to introduce quantum computing. For this perspective is currently studied. So the direction for R&D for us is that as short as possible, near-term usable algorithm is what we want to develop. For example, the lesser bits, lesser operations, more noise immunity bound algorithm is the target that we are now trying to develop. Then, when it comes to simulation, how the research is currently ongoing, let me introduce you with that. This is the overview of simulation research. The background for that is that, well, derivative financial instruments, that is the derivatives from the stocks and also bonds. And for the price decisioning, every day many hours are spent for the calculation of the price using parallel computing. And this is where the calculation time is utilized the most. So we would like to shorten this time. And the conventional method of calculation is the ups and downs of the future price. Like you can see on the right top, the probability-based price fluctuation is simulated, and based upon that, the mean is taken to decide the price. So this future price change scenario, the more we have of such a scenario, then accuracy is increased. So Monte Carlo calculation is the method introduced for the calculation. When it comes to quantum computing, then we can introduce the quantum amplitude estimation algorithm. With using this calculation can be accelerated in a squared manner. But for this, the number of the bits, number of the operations are quite large for this approach. So in order for making this real, we need to do the improvement. So that's also where we got involved for the research. More specifically, this is what we do. This quantum amplitude estimation algorithm has been continuously improved so that it can be tolerant for further noise. Algorithm is being improved one after another. Around 2000, this QAE, or quantum amplitude estimation algorithm, was proposed, but in 2019, 20, 21, continuously that is improved, especially as a part of IP strategy 2020, we came up with the patent that was registered. And what kind of improvement has been introduced? I'll be explained from the following pages. This is 2019, the very first improvement. The conventional method is that for amplitude estimation, all the calculation is done on the quantum computing. But as you see left bottom, more specifically, Glover algorithm has been introduced, and the sequential calculation will take place for quantum calculation to get the final result. But the current, if we want to do this with the current computing, well, because for the computation, noise is applied. Therefore, ultimately, there are so much noise, and the result would be compromised. Therefore, in 2019, we proposed a new method. Overall, computation is divided into some, and quantum computation is introduced only in the area where that kind of technology is necessary, and others are done by the classic computing. So it is divided, so the quantity of the usage of the quantum computer was way reduced. So this is a separated execution. And you might wonder, in this case, the performance might be compromised to a certain extent. But with the statistical estimation theory, we were able to confirm that this approach does not reduce the performance. As you see here on the slide, the method has been introduced. So we came up with the algorithm of this method that does not compromise the performance. And also we did a calculation numerically, and that matches the theory. Horizontally, this is a Grover operation, and vertically, this is the accuracy. And black line is theory, and the black dot is actual calculation, and then they match each other. With this algorithm, the number of the operations or calculations were able to be reduced. As you see on the left, horizontally, this is a Grover operations, and vertically, this is C0, heavy calculation, compared to the existing one, that is a red. The proposed method was able to reduce the burden by 1/20th. And also bits. Also, although I didn't explain, but we were able to reduce the level of the bit to a certain extent. So there's such an improvement took place. This happened in 2019. And with the actual machine of the quantum computing, and we tried to introduce this 2019 algorithm. Due to the noise, the result is distorted. So we have to take noise impact into consideration. So we came up with this new approach, 2020. Well, 2019, that is a noiseless impact. But our new algorithm at that time is the amplitude estimation method considering the effect of the noise. So they are modeled as noise with a constant probability for each operation. If this modeling is right or not, we confirm that. We utilize the IBM quantum computer machine, and we learned that this model is likely to be right. The horizontally global operation frequency, vertically this is the output probability. The dot is a real device, and the blue line is a depolarizing model, and those are almost overlapped, meaning that this model is almost appropriate or rational. Now we learn about the kinds of the noise. So with using that, to what extent of performance can be realized is shown here theoretically on the left side. This horizontally Grover operation, vertically accuracy toward the bottom, that means the accuracy is good. Orange without noise, and red is in the case of Monte Carlo calculation. Green, blue, light blue, with reducing the noise, it comes closer to orange line, that is without noise. But quantitatively, to what extent noise should be reduced so that it can be further closer to orange line is described here. This green line at the very top, well, that never comes lower than the red line, but the blue and the light blue, they come under the red line. Even with noise, it can go better than the red line or classical computation. And the right side, this is actual calculation with using IBM equipment that is described here with the blue dot. And you see blue dot comes lower than the red line, even with the noise compared to the classic computation calculation accuracy is better. That's 2020. The next comes 2021 improvement. Well, in 2020, all operations or calculations are impacted with the same noise. But with the current quantum computing available in the world, and for each device, noise is different. So if you want to use all the machine in a parallel manner, you have to face the problems of the different types of the noise. So in order to deal with that, the research was conducted in 2021. Well, in order to identify noise, auxiliary circuit is newly introduced to deal with different noises. This auxiliary circuit is introduced, and due to that, the computation will be increased. So that's one of the concerns. But with the introduction of auxiliary circuit, actually there is almost no overhead. That's on the left bottom. Without auxiliary circuit, green with auxiliary circuit blue, and they are overlapping mostly, which means there is no extra overhead. And many noise models are introduced more, meaning that you have more parameters. So the later process is going to be more complicated. But we use the parameter orthogonalization method. That is a classic method that allows to solve the problems, even in the presence of many types of noise. That was confirmed. That's the update of our algorithm. And on top of this, at the QC where some improvement took place, and within this paper, they assessed the utility of algorithm with QC where. That is the original amplitude estimation method. And that is often applied for clipped analysis. So we consider that the clipped analysis comes faster as a real-world technology, but with a combination of our improvement as well as QC, where it is likely that the amplitude estimation comes earlier as a practical way to do the computing. This is already incorporated into our open source framework, QSKit, and also here is a tutorial URL. And if you refer to this, you can learn about how to use it, and you can directly use it to try on IBM quantum computer. That's a global operator's improvement, especially for the amplitude estimation. And there, Grover operators are assumed, and based upon that, we did some improvement. But on top of that, we are working for further effort for the improvement with the further noise. One of such is the improvement of global operators, and also making the readout of the data efficient is something we are doing in 2021 and 22. So let me introduce you that as well. So data is read into the quantum computer for the calculation. With the standard method, quantum computers you have to do a lot of the operators and quantum operation with high frequency will be necessary. That's a problem. Well, the standard method, first of all, is to read in the process data, but to a certain extent of approximation is adapted. And with that, with a small number of the calculation, you can put the data into the quantum computing. And this is 2022. Dr. Yan from Tokyo University gave us the guidance for this research. This is about the efficient correction of noise during data readout. With the current quantum computing, there are various noises. The biggest noise, one of the biggest noise, is the noise at the time of the data readout. And the noise there, generally speaking, against the bit, the exponential amount of time would be necessary. So if it is more than 50 bits of the correction in quantum computing is not realistic, 170 bits of quantum computer is available from IBM. So solving this problem is one of the indispensable things that we need to do. So here we introduce a more realistic approach so that efficiently we can improve this. 65-bit GHZ status correction. Well, this is the size issue. Even a supercomputer cannot deal with this. But the 2015 MacBook Pro or no PC, this can be corrected within just 5 seconds. And with using IBM machine, the biggest GHZ status became realized. And this is registered into the international benchmark site metric. Regarding this algorithm, as Python library, it is now under the preparation. You can combine with the different types of the quantum computing packages so that can be used. Summary from me. These quantum computers are technology that has a potential to bring about a major game change in the future. Mizuho views technological developments and other changes in the environment as opportunities to create innovation, and Mizuho is actively pursuing the latest technologies such as quantum computers. Quantum computers are developing rapidly, and now is an interesting time because we can try algorithm, However, the key to utilizing quantum computers in the near future is how to deal with noise. This is quite an important point. And the research introduced here was born from the perspective of wanting to have financial problems somehow with noisy devices. So very active approach is going to be quite important for sustainable corporate growth. That's all. Thank you very much.